Hi, so I just wanted to talk about some of the math stuff that I've been studying lately. So I'm not an expert on these topics because if I were an expert, I probably wouldn't be studying them. So it's kind of the edge of my knowledge. So first, I want to talk about geometric meaning of trace. Trace in linear algebra, the trace of a matrix. So like here, you add up the elements along the major diagonal, so you'd get 2 plus 3 plus 1, so you get 6 here. So that's the question. What is the geometric meaning of that? And the second thing I want to talk about is, I guess, Einstein-Cartan theory. It's kind of possibly more a more general version of general relativity. And yeah, I wanted to talk about this post also. So, okay, so about the trace. So if you Google this geometric meaning of trace, you get this math overflow thing, which I'll talk about. And then second result is this Medium post, which I have not read yet, but I plan to after recording this. So this is what I was looking at yesterday. Now, some of you probably know that the determinant of a matrix is, very nicely linked to areas and volumes. So it's kind of, see, this volume being traced out by vectors is roughly equivalent to that. Let me see. I had it in Blender, but let me just show you. Parallelepiped is the shape. So, yeah, I don't want this to be just about the determinant. But it's a very useful thing that you can calculate for a matrix, and basically it's going to be, in general, it's going to be the volume of a parallelepiped, this kind of shape. It's like the 3D version of a parallelogram, basically. And so in 2D, it's just a parallelogram. But in 3D, in general, it's this volume. And so the determinant basically tells you how much. So a matrix, you can view it as a transformation. So it's sort of the linear maps on a vector space, from a vector space to itself generally, but it can also be, so if it's a square matrix that is not degenerate, which means that the determinant is not zero, then that is a map, a linear map from a vector space of n dimensions to itself. So we're basically talking about the ways in which a vector space can transform. So obvious things are scaling and rotation. So for rotation, the determinant is 1, meaning that there's no scaling, essentially. But there's, and then the other thing that is happening is basically shearing, where, like, if you started with a rectangle, imagine the 2D case. If you started with a rectangle and then you just sort of like take the top of it and just move it horizontally, shifting it into a parallelogram, that's a shear. So we can kind of break apart what kinds of things we are doing when we do linear transformations. In other words, what kinds of things matrices can do. So this whole discussion is sort of the way to gain an intuition of linear algebra and what matrices are doing. And there's also the trace of a matrix, and that has become important in some of the other stuff that I've been doing lately. So I really, really want to understand this geometric interpretation of trace. So this question, which is pretty popular on Math Overflow, says, this afternoon I was speaking with some graduate students in the department, and we came to the following quandary. Is there a geometric interpretation of the trace of a matrix? So the fact that, and this sounds like they're a professor, maybe. And so the fact that they're having this conversation with graduate students, probably in a math department, and they don't immediately know the answer tells you that, okay, this is not a trivial question, and it's probably an interesting question. So this question should make fair sense because trace is coordinate independent. Okay. We were hoping, yeah, so he talks about determinant, and we're hoping, I always say that for some reason. We were hoping for something like determinant is the volume of the parallel pipette spanned by column vectors. This is what I just described before. So, yeah, that's nice. Indeed, this is really, really important to understand in linear algebra. This is like the first thing really where you go, aha, now things make sense once you understand that. Okay. So also after looking at the wiki entry, I don't get it. Maybe I'll look at that later. Yeah, so it's a bit complicated. And actually, I've read through these responses, and I don't really understand it. So if your matrix is geometrically projection, algebraically a squared equals a, then the trace is the dimension of the space that is being projected onto. This is quite important in representation theory. So representation theory is where you study Lie groups, which I've talked about here before, and you represent them with matrices. So I do need to study projection matrices. I understand that they project one vector space onto another. You can kind of think like if you had 3 dimensions and then you squash it onto 2 dimensions, some plane within that space, that would be an example of what a projection matrix does, I think. But I don't quite understand, even though that's the top answer. And then we get, this is a little messy, I'm not going to lie. This one mentions Arnold, and that's a famous mathematician. Let's see. Suppose small changes are made in the edges of a parallelepiped. Then the main contribution to the change in volume of the parallelepiped is due to the change of each edge in its own direction. So, okay. Changes in the direction of the other edges, making only a second order contribution to the change in volume. So what I don't quite understand, like I read this before. So this tells me that this discussion of trace may have something to do with the derivative, because we're talking about small changes being made. And I presume you can talk about the derivative of a matrix, but I don't know exactly what that looks like. And so they're talking about taking this parallelepiped and moving, how do I drag from this side? Whatever. Moving an edge, right? Change in volume of the parallelepiped is due to the change. Okay, the main contribution to the change in volume is due to the change of each edge in its own direction. Changes in the direction of the other edges. I can't visualize exactly what they're describing here about the moving around these edges. I don't get it. Okay. This one talks about Hermitian matrices, which is even a little more complicated than what I want to think about. That has to do with complex numbers. Okay. Matrices with complex numbers. I read this one, but I don't quite understand this one either. Let's see. We calculate the trace of A as blah blah for any choice of orthonormal basis. Then they have some integral. Again, I don't understand. There's one answer way down here that intrigued me. And it brings up, connects things to category theory. Where was it? Do I have to dig this far down? Maybe I skipped over it by accident. I must have skipped over it by accident. Pondered over this question quite a bit because I love the geometric definition of the determinant. My current feeling is that though the trace has a beautiful geometric meaning, the one given by Alan Knudsen. So Alan Knudsen, which one was that? This one. Let's use determinant. So we have an exponential e to the ta equals 1 plus, oh, this is so confusing. If we take a unit parallelepiped worth of y0 flow for a short time t under this and see how its volume changes, the change will thus be t times trace a to first order. Took me a while to understand what you meant by a unit parallelepiped worth of y0. To clarify for future readers, you are starting with the unit parallelepiped and flowing each of its n orthonormal unit vector sides that independently under the vector ODE that. Okay. So the parallelepiped's time evolution is given by the n different solutions of that ODE. Change will thus be t times. A few light bulbs went on here, but not quite understanding. But they're talking about some kind of flow. Because when you take e to the, like a matrix like this, and you put it through the exponential map, this can be viewed as a sort of a vector flow. I'll have to think more about this. We'll see how its volume changes. The change will be t times the trace. So it sounds to me like if we put a matrix in, multiplied times some scalar, which we're counting as time, and we put that through the exponential map, we have this vector flow stuff going on. So you have to imagine a parallelepiped like this, and there's vector flow. So imagine it's like when they're talking about weather on the news, and you have they show like wind flow going around. That's like a vector. That's basically like vector field or vector flow. But you imagine that in 3 dimensions here. It doesn't have to be 3 dimensions. It can be whatever. But then you now imagine that, so let's say it's slightly expanding, this parallelepiped with time. Then, so you imagine this parallelepiped expanding. And the rate of change of that volume will be t times the trace. That's what it sounds like here. So that's okay. That's interesting. Maybe I kind of get it now. But somewhere in here, somebody was talking about category theory. But I'm not seeing that. That's part of what I wanted to talk about. This is it. Shadows and traces in bi categories. So this is the paper I was looking at. It says subject category theory. And this was motivating me to study some category theory. And then I believe I looked for duality category theory. And it's actually this playlist that's pretty good. So I've studied category theory a bit. It's almost kind of sort of the most general abstract thing in math. And it's not very easy to learn. But yeah, so there's no easy way to learn it, really. But this playlist was actually really good. Category theory for beginners. Though I don't think it's not like you watch through this and then you're a master of category theory, but this is a pretty good series, that's all. Yeah, it's a tough one, category theory. But anyway, I wanted to study this paper. The purpose of this paper is to study and exposit a categorical notion of trace. Da-la-di-di-la-di-da. So often in category theory, there's often dualizable objects, or I think they're called, maybe they're called dualizable categories. Anyway, there's certain categories that have this concept of a dual. So I was reading through this, and I don't know category theory that well, so I was then thinking I'll learn category theory so I can understand this, so I can understand the trace, but it's a long journey. It's a long journey. But I mean, if you understand category theory, I don't think that these charts are very difficult. Then you get to this kind of stuff. This kind of stuff. This kind of stuff. And they have some really weird, complicated ones at some point. I don't know, this paper seems interesting though. I'd like to try to understand it. It's going to take a while. I might have skipped over. There's something I wanted to show. Anyway. Yeah, and then I was going to talk about this Cartan stuff, but I guess I'll make a second video for that. In the future, I might talk about category theory, but I am not an expert on it, so I'll have to be a little vague, perhaps. Anyway, that's it for now. Thanks.